Hello everyone, my name is Anna and I have my little friend Boris here with me. Um, I'm almost finished with lesson 7 and I have finished lab challenge. I'm still working on improving my model though. I want to thank everybody who joined me for our live webinar early. We had some technical difficulties, so I decided to go ahead and re-record it and make a link available. So I want to apologize to those who could not see or hear me during webinar, and I want to apologize to those who could see and hear me during webinar. Because I spent too much time on trying to figure out what's wrong with the platform. It was my first experience with live webinar on Zoom, and I really appreciate you guys being patient, sticking out with me, listening to me, and just thank you for your patience and understanding. My webinar is about sigmoid and softmax functions in context of neural networks, and to be more particular is about conceptual understanding of sigmoid and softmax functions. I believe that when you understand concepts, like understand a bigger picture, you have less problems dealing with math, because sometimes math could be very intimidating, but if you understand the concepts behind it, the math appears much less scary. So my goal is to explain softmax and sigmoid functions, concepts behind them, and maybe that would help with math. So softmax function and sigmoid function, they are used as activation functions in neural networks. So what does it mean? Why do we need activation functions? Can we do without activation functions? Well, to answer those questions, I would like to go back to our basic perceptron that consists of 4 parts. We have our input right here. We have our, hold on, I'm backwards. We have input, we have our weights and bias, we have our weighted sum, and that is fed into our activation function. Okay, so let's think for a moment. What is perceptron? Well, it's actually artificial neuron, and artificial neuron based on biological neuron. So our perceptron, our artificial neuron, needs to be able to do what biological neuron can do. And our biological neuron basically has ability to fire or not fire, to get activated or not to get activated. That's where our activation function comes in. Help our artificial neuron to get activated, to produce output. So our activation function is actually decision-making function. Well, let's look at our perceptron if we did not have activation function. So say we have to make a decision based on our weighted sum. Can it be done? Well, let's think about what is the range of our weighted sum. It's actually minus infinity to plus infinity. Not a good range to make a decision. So that's where activation function comes in. Activation function also is called transfer function. So basically it transfers our weighted sum of our weighted values into decision on output whether our artificial neuron is activated or not activated. In our perceptron, activation function is step function. Let's look at our activation function, step function, a little bit close. I know you guys seen it, but I just want to present it one more time. So our step function has output of 1 when our input values 0 and above 0, and it has output of 0 when our input values are negative. So for positive input values and 0 is 1, for negative is 0. That's a great decision-making function for binary classification. So say if we had a model where we want to make a decision yes or no, that's what our step function does. Yes or no, 1 or 0. That's great, right? Well, let's think about it. Say we have more than one class, and say we have more than one neuron, and all those neurons get activated. So they all have output of 1. How do we come up with decision? It would make it much easier if our activation function would produce not binary output, but say something like 30% activation or 20% activation. Then you can have more than one neuron activated, and then you can look and find neuron with highest activation value. So that's how we're gonna jump into sigmoid function now. So let's look at our sigmoid function. So our sigmoid function, when we looks kind of like step function, right? Yeah, doesn't it look similar, kind of, sort of, right? So intuitively we can come up to conclusions that sigmoid function would be a good activation function. Okay, so let's keep talking about it and thinking about it. Sigmoid function. It also, if you look at it, it's non-linear. World around us is non-linear. So if we want to build some kind of decision model, we have to build in that non-linearity of our surrounding world. So using non-linear activation function is a great way to introduce that non-linearity into our model. Sigmoid function also, just like step function, squishes our output between 0 and 1. It puts that boundary, so it's not gonna explode out of control like I was talking about weighted sum, which has a range between minus infinity to plus infinity. So being between 0 and 1 is a great range to give us probabilities. So sigmoid function centered around 0.5. It's very symmetrical. So we can also make decisions that anything that above 0.5 has this yes, basically output, and everything below 0.5 has no output. Also, sigmoid function is differentiable, which means that it's pretty easy to take derivatives. We need those derivatives to calculate gradient descent, which we use during training. And derivatives is basically a slope, rate of change. So we don't have a sudden rate of change like we have in a step function right here. Sigmoid is a smooth function, continuous smooth differentiable function, which is great to be used as activation function. So there are some problems that could come up with sigmoid function, and I want to talk about them. And basically, it's when we start going towards either end of sigmoid function, our values start responding less and less to changes in our our axis. What it means that our gradient is becoming really small. That is what we call vanishing gradient, problem of vanishing gradients. And it could present problem during training our model. Okay. Now I want to go ahead and build a bridge to our softmax function, and I'm gonna do it by saying that softmax function and sigmoid function for two classes the same thing. Okay, and I'm gonna show you how it works. So I'm gonna start by sigmoid of two classes. Okay, I'm gonna have -2 right here, my two classes, and I have exponent of -2. That -2 will kick my exponent into denominator, so I will have that kind of function, which we're gonna have a common denominator over here, exponent of 2. So that's what I'm gonna get. That exponent of 2 is gonna be kicked up into numerator position. Okay, and I will have exponent of 2 over 1 plus exponent of 2. My 1 over here is basically exponent of 0. Okay, so I'm gonna write it out, and look, we arrived at softmax function for two classes. Okay, so softmax function is great for classification of more than two classes, multi-class classification. Okay, and probabilities in softmax function sum up to 1. I would like to illustrate the concept of softmax function, and I'm gonna use all well familiar to us duck, beaver, and walrus. Okay, so I'm gonna say that I'll start with probabilities for duck, beaver, and walrus. Duck will have 0.67, beaver 0.24, walrus 0.09. And those just example numbers, they are just for illustration purposes. So our probabilities have to add up to 1. Okay, say we have a model that produces scores for our duck, beaver, and walrus. So right here we're gonna have duck is gonna have score of 2, beaver is gonna have score of 1, and walrus is gonna have score of 0. Okay, but we need to have this add up to 1. So what do we do? What does our activation function needs to do? Well, one approach we can take is divide our scores by the sum of all scores. So say 2 divided by 2 plus 1 plus 0, 1 divided by 2 plus 1 plus 0, and you can see for walrus. Okay, that's a great idea. However, if our scores are negative, we can run into some problems. Say over here we had say -1 and another -1. We actually can wind out with the problem of dividing by 0. Not good, not good at all. So what we're gonna do, we're gonna use exponent function. So here how it's gonna look like. So for duck with a score of 2, we're gonna have exponent of 2 divided by sum of exponent of 2 plus exponent of 1 and exponent of 0. We get our probability 0.67. Beaver is gonna have exponent to the power of 1, exponent of 1, divided by exponent of 2 plus exponent of 1 plus exponent of 0, gives us probability of 0.24. And Walrus calculated the same way, except we're going to have our, remember, our score for Walrus is 0, so we're going to, I didn't put it right here, so I should do it so as not to confuse. So Walrus is 0. Here, that's where 0 comes in. So our probability is going to be 0.09. They all add up to 1, which is great. So that's the idea behind softmax function. And softmax function is great for multi-class classification. Okay, so I want to thank you guys for joining me for this webinar. Please don't hesitate to contact me on Slack if you have any kind of questions, follow-up questions about webinar or about challenge or anything. I'll be more than happy to help you. So good luck with the rest of the challenge. And Boris, say bye. Well, Boris has better things to do. All right. Well, guys, thank you very much. Good luck.